Hi, kids. All right, so what I'd like you to do is have your books out, open up to page 120, and I'm going to have you start the warm-up as if we were in class today and I was there. So what you're going to do is state the domain and range of both functions, so the original f of x function and the inverse function, and make sure you rewrite both functions and then find each domain and range. Take a second, pause the video, work on this, and then when you're finished, start it back up. All right, so what you should have to start off with, seeing how the first function is a parabola with the x squared plus 4, what I would do is just draw a little function just to help us out and understand that this plus 4 means it's a vertical shift up 4 units, and the a value is positive. So we're going to increase, and our domain is going to be from negative infinity to positive infinity, and the range, because it was shifted up 4 units, is going to be from 4 with the bracket to positive infinity. Now, for the inverse, what you should have here is we first want to redo our inverse. We want to make sure that we rewrite it as y equals x squared plus 4, and then we switch our x's into y's. So we're going to go x equals y squared plus 4, because this function right here, this is our inverse. So it could be finished, but we want to always resolve it for y. So I subtract 4 on both sides. So I'm going to get x minus 4 on the left equals y squared. And then lastly, take the square root for both sides, and my inverse function is f inverse of x equals, and then what we get here, the square root of x minus 4. Now, after we find the inverse, we want to make sure that we still answer the question, find the domain and find the range. So the domain of this function, because it's shifted, this is a square root function, so it has a horizontal shift to the right, 4 units, 1, 2, 3, 4, so boom, it goes to the right 4, and so goes up and to the right. So our domain starts at 4 and goes to positive infinity. And then our range is, because there was no vertical shift on it, it's 0 to positive infinity. Now I apologize, I don't know what's going on. This is the first time I've had to write and do this, so there are some things that are a little goofy. It's like putting some marks on here, but hopefully we're getting the main gist of this. So, all right, that was our warm-up. Normally we go over homework. The homework answers were in the back of the book. Make sure you check through those. If you have any questions, we can go over those tomorrow in class, or actually Thursday. What I'd like you to do right now is flip your book, and we're going to start today's lesson. We're going to start on page 126. This is a review from last year. It should be. I know that because I'm teaching this currently in Math 1, so I know that you learned this, but I'm just going to recap and re-go over this because it is essential for this entire year. So here we go. Exponential growth and decay. So on page 126, I want you to write the function y equals a times b raised to the x power. Now you have learned about one other exponential function that is very similar to this, and this is y equals a parentheses 1 plus or minus r raised to the t power x power. These are virtually, literally the exact same equations. This b value is the same as this 1 plus or minus r. When you were in Math 1 last year, you used this function with the r in it when you had a percent rate, like 2% growth, 6% decay, all that stuff. So anytime you use percents, you use this. But now we're going to do big boy, big girl math, and we're just going to use y equals a times b to the x power as our primary exponential growth and decay function. So anyway, so again, understanding and remembering what these values are. So y is our ending value. A right here is your initial amount. B is your growth or decay rate. All right, it's your growth or decay. So you have to actually know and look at that B value to determine, is it exponentially growing or exponentially decaying. Now, when we do this, when we are looking at these values, all right, I have here kind of staying the same as what we've done in the past. 1, which means 100%, when you have a value that is greater than 1, like 1.01 or 1.23, that 1 isn't part of your growth. That just means that we are increasing our value, and you're looking at the decimal that follows. So any value over 1 is a growth. Any value that's over 1 is a growth, and any value under 1, less than 1. So an example of this would be like where's the pen? like 0.82 or 0.07. Those are all decays. Growth would be like 1.23 and 1.05. Anything that's over 1 is growth. Anything less than 1 is decay. All right. Now, one thing that we need to remember is, yeah, it's growing 1.23, but what does that really mean? So the 0.23, that actually is your percent. This is your percent that you're growing. So 0.23 really means 23% growth. This 0.05 really means 5% growth. And that's just knowing how to convert decimals to fractions and vice versa. So now when you look at decay, all right, this isn't an 82% growth. What this is you have to go 1 minus 0.82, and that equals 0.18, which means this is an 18. This 0.82 really means it's an 18% decay. D-E-C-A-Y. And this 0.07, that's really a 93% decay. So it doesn't mean 7% decay, it really means 93%, because you always got to go 1 minus that. It's the value less than 1. So just a nice little review from Math 1. And then lastly, so we had A, that's your initial amount, B is your growth or decay, and your X is your T. Your exponent is always your time. Now notice in the original function, your coefficient of your time, your X, is 1, and that's what it always needs to be to understand what our growth or decay rate actually is. So let's go on to the notes for today. Let's flip the page. Here we go. So what I want you just to do is take a little look, see if you can understand which one of these 5 functions that are up here are growth or decay. Pause the video, take a second, see if you can go through and say, hey, that's growth, that's decay, growth, decay. And after you've figured it out, play it and we'll see where it is. All right, so hopefully you figure this out. When looking for growth or decay, what you want to be looking at is you want to be looking at the number inside your parenthesis here. So you want to make sure that you are looking constantly at your B value, or your number that's inside your parenthesis here. So that's what I'm going to be looking at every time that I do growth or decay. So for this first one, the maroon function, this is a decay because our value inside our parenthesis is less than 1. This is actually a point, so it's less than 1. It's a 33% decay because it's 1 minus this number, so it's 33% decay. This blue or light blue, this is a decay also because it's less than 1. This is a 19% decay because 1 minus is 0.81 or 0.81 is 0.91 or 0.19, which is 19%. So this decay. The navy blue one, this is a growth because it's greater than 1, and that's a growth of 12%. The royal blue, this is a decay because it's less than 1, 0.95. This is a decay. It's actually a decay of 5%. And then lastly, the red one, that is a growth function, and that's a growth of 3%. All right, notice I don't care about the numbers on the outside, my A values, my initial values, don't care. I look at the numbers on the inside, the parentheses, to determine growth or decay. All right, so good. Hopefully you all got the 100 on that. So here's example 1. So it really is just looking at the next page over. So this is our first example. It's tracking schools' population. So it says the school uses the change in the total number of students to estimate how many students have been enrolled in the school each year since the year 2000. If T is the number of students after the year 2000, the number of students F of T can be estimated using the function. And here we go. This is a function. This is what you want to be kind of looking for in all of our problems. F of T equals 250 times 0.98 raised to the T power. Now, here's the question. It says, how is the number of total students changing each year? Is the total number of students growing or decaying? So there's a couple questions, so you got to make sure you answer all of them. Now, this is a scaffolded problem, so it's really going to kind of tell you what to do for each problem, but you want to get better at understanding what's what and what are they asking for. So number 1 says, identify the yearly rate of change. So we're going to take our function, and in this function, the yearly rate of change is your B value, which is 0.98. Now, we should have learned from the last 2 slides that this is a decay. And that looks awful. I don't know why it's doing that. But anyway, it's a decay because this is less than 1. Now, it's a decay of what? So to determine, you go 1 minus whatever your B value was, so 0.98. And when you do that, 0.98 or 1 minus 0.98 is 0.02, which is a 2% drop. You are going down. You're decaying by 2% each year. So the second thing says, describe how the rate of change relates to the dependent quantity. Well, the dependent quantity, all right, is the number of students. So your dependent quantity is the number of students. So if we're dropping 2% each year, what's happening to our population? The number of students goes down. So enrollment is decreasing. So it should make sense. Yeah, of course, it's decaying. We're losing the amount of students that are in our population, and we're losing 2% each year. So, all right, good. Now go to page 126, and that's where we were taking notes before, and I want you to write this down because this is actually the new stuff, all right? This is called power of a power property. Now, whenever we are doing exponent problems, you have to make sure that your power, your exponent, is always raised to 1x. Now, in this first problem, we have y equals 0.83 raised to 3x. Now, if you look at it quickly, you're probably saying, hey, that's a decay. This is a decay right here of 17% because it's 0.83, it's less than 1, 17%. Okay, but unfortunately, it's not actually a decay of 17% because our exponent is raised to the third power. This is actually an incorrect value. What we have to do is we actually have to readjust our equation and resolve our equation for our new b value by moving this 3 to the interior by using the power of a power property. All right, that's an exponent property where we can move exponents or distribute them into your parenthesis. Because to really evaluate this function, know what the growth rate or the decay rate is, you have to move that exponent on the inside and then re-evaluate it. So what you would do is you put 0.83 into your calculator and you simplify it and you get 0.571787. So truly, this is a decay. It still stays a decay, but it's a greater decay. This is approximately, I don't have my calculator on me. It's kind of weird, and I don't know why it's writing that, but this is approximately, geez, come on now. Where's my eraser? This is why I shouldn't. What is going on here? This is so weird. Anyway, it's approximately 43%. So it's approximately 43%, and I'm trying to write that down, but of course it won't. Approximately 43%. Now, many of you are probably saying, Mr. Qualman, your handwriting was awful in class. It is going to get worse, so stay with me here. So what I want you to do is I want you to try to simplify this. So write this down, pause the video, and simplify it to see what the new b value is. All right, so hopefully using what we just learned, the power of a power property to reevaluate this, this is not a 9% growth. What we have to do is we have to distribute this 7 to the inside of here. So we're really going to get y equals 1.09 raised to the 7th power x. So when you simplify this 1.09 raised to the 7th power, you should get y equals, and now we're going to get a new b value. You should get the b value 1.09 raised to the 7th power of 1.828. Oh my goodness, this is awful. That looks like an 8, but that's a 2. 8 raised to the x power. So really, it's still a growth, but it's actually a growth of 82.8%. So it's a much greater growth than 9%. So you have to make sure that you distribute that exponent when it's not 1 to your b value so that you can solve. All right. So hopefully you can bear with me. We only got a couple more problems. This writing is awful, by the way. All right, here we go. Page 128, 2 more examples. Here we go. So it says a bank offers a savings account with an interest that is compounded monthly. In other words, the interest earned is added to every account every month instead of once a year. Dylan opens a savings account with $500. If T is the time in years that the account has been open, the balance of his account F of T is F of T equals 500. So here's our equation that we want to be using. 500 times 1.004 raised to the 12t. So I'm actually going to write that out because we're going to be using that down here. So 500 times 1.004 raised to the 12t. Now, there's a couple questions. It says, what's the estimated yearly exponential growth rate describe how this rate relates to the yearly change in the balance of Dylan's account. So first off, you cannot say it's a growth. We know it's a growth, but we don't know how great it is because notice our exponent here is raised to the 12t, not to the t. So we have to actually distribute and put this 12 inside of our b value. So we have to reevaluate 500 times 1.004 raised to the 12 t, and now we reevaluate. So it should be 500 parentheses. So when you type that in calculator, 1.004 raised to the 12 power, and you're going to get 1.04. So we're losing a 0 there, and then 907 raised to the t power. So if you look here, now we can start saying, all right, it's exponential growth still, but what's our growth at? So if you look here, this is our growth, but what's it at? Well, I should use these. This is why I wrote them. No, it's an increase of 4.9% because 0.4907 is approximately 4.9%. So if our bank account is growing at 4.9%, what is that going to do to the amount of money that I have in the account? Well, hopefully we should all know this. If your account is increasing, so should your balance. It should increase about 4.9% each year. So hopefully that makes sense to us. But the big thing here is we cannot say, oh, it's growing by, really, if you look at the original problem, if we didn't distribute that 12 in there, you would be saying it's actually like 1/4%, or not 4/10%, which is like less than half of 1%. So there's a big difference, less than 1/2% to 4.9%. So it's important that we use the power of a power property there. And here's our last example of the day. So it says number of bacteria f of t at any time t in hours can be estimated using the function f of t equals 3,000 times 1.24t. So automatically, I know I got to be using this equation right here. So I'm going to rewrite this actually down here. So 3,000, gosh, this is awful, 1.24 raised to the t power. So what is the initial size of the bacterial colony? Is the bacterial population exponentially decaying or growing? Well, first off, let's look at that exponent. Is it raised to the 1t? And it is. So that means we can look at this b value, and this is a growth. And it's a growth of, and this is when you look at just the decimal here, of 0.24, so it's a growth of 24%, right? Now, so that is the percent population that's exponentially growing by 24%. Now the last question says, what's the initial size of the bacterial colony? Well, we haven't talked about this since when we first started taking notes. The initial size is your A value. So our initial amount is 3,000 ants. So if you look here, we increased 24%, it's exponentially growing, and we start with 3,000 bacteria. So we are done with our lesson for today. What you are going to do is you are going to turn to the homework page. I believe it's like 2 more pages, and you are going to do 1 through 10 and make sure that you're checking your answers in the back of the book. If you have any questions on this, you may come in early on Thursday. Don't come tomorrow or Wednesday. Enjoy your days off, and make sure that you are getting that homework done and enjoying your 2 days off. All right, kids, take care. I apologize for not being here today, but hopefully this was a nice, easy lesson that me being there really doesn't matter. All right, take care.